Hello, this is Jennifer Martinez, and today we're going to talk about the tangent line approximation. The tangent line, since it lies so close to the actual function when we're close to a point, we can use this to approximate the function value. So here's the formula in the book. It says for x near a, f of x, the actual function, is approximately equal to f of a plus f prime of a times x minus a, which on the right-hand side, that is actually just the equation for a tangent line. We'll see in a second. So what this is saying is, if you're at a point A onto some function, let's call this f of x, and you draw the tangent line, so here's the tangent line, the values of the actual function near A is approximately the same values as the tangent line. So you can get this formula very easily by taking our equation of a tangent line, and we have the point A comma f of A, and we'll call the slope f prime of a. The slope of the tangent line is f prime of a, and we just plug this in here. So this would be f of a, this would be f prime of a, and the x1 we have as a, and you just solve for y and you get the formula. So this is, I'm going to call this y of a because that was the tangent line that I found. So that's approximately f of x near x equals a. We have it. So let's go ahead and try this example. Given f of x is equal to x to the fourth minus x squared plus 3, let's approximate f of 1.04. Since at x equals 1, 1 is very close to 1.04, that's what I'm going to let my a be. Which, by the way, is very convenient to find because f of 1, we know we could just see is going to be 3. And f prime, well, let's do f prime of x first, just to figure what the formula is. That would be 4x cubed minus 2x. The derivative of 3 is 0. So f prime of 1, we know it's just 4 minus 2, which is 2. We have all the pieces. We could say f of x is approximately equal to f of a, which is the 3, plus f prime of a, which is the 2, x minus the a, which is the 1. That is our tangent line approximation. Or you could have just found the tangent line, not used this formula for the point 1 comma 3 and the slope is 2. That would have worked as well. Now if I plug into 1.04 just in this form, you can see what's happening. This would be 1.04 minus 1. So f of 1, let's make that approximately. F of 1.04 is approximately 3 plus 2 times 0.04, and that would be 0.08 is the approximate value for f of 1.04. Let's see how close we got. Let's plug in 1.04 because we can actually do this because we actually have the function value, and just see how close we are. So if I put 1.04 in my calculator, we get 3.088. So pretty darn close, you can see here, to the actual value to this tangent line approximation, because 0.04 was very close to 1 at that spot. So let's look at an application. You can actually predict future values. This is really actually useful if you don't even know the function, but this is when we're given the function. So the power generated by a wind turbine is proportional to the cube of the wind speed. So we have this value, where K is a constant that depends on size and design. The North Hoyle wind turbine off the coast of Wales in UK has K equals 2 for the power in the kilowatts and the wind speed in meters per second. Find the tangent line approximation at V equals 10. So we know at V equals 10 you can plug in the P, so that would be the point, 10 comma 2000. And the derivative we know is 6V squared. So if we're looking at V equals 10 there, that would be 6 times 10 squared, which would be 600. And then we can use our tangent line approximation. We know the tangent line is going to be, well, we know it's f of a plus f prime of a times x minus a, where the a is equal to 10 this time. So the f of a we know is the 2000 plus the f prime of a we found is 600. We should call x v since they're not using x's here, so let's call that v minus the 10. There it is. And this is approximately equal, we'll change it to this, because now this is approximately equal to f of x. So we'll just say this is approximately equal to, we'll call it p of x. So that is part A. That is the formula. So now we can use it for B, and we can say use this tangent line to estimate at 12. So if you estimate at 12 here, P of 12 is approximately, plug it in just at 12 here, so it's approximately equal to, that's a 2, and that would be 1200. So you can see that you could predict what the future is going to be, right? We're going to estimate the power generated when the V is 12. And this is what this is right here. And that would be in kilowatts. So what happens when the V is 9.5 meters per second? Well, you could do the same thing. It changes by negative 0.5, so that would be a negative 0.5 here, plugging in a 9.5, or negative 300, so it'd be approximately 1700 kilowatts. Now, these values aren't quite as close as the example I did before, so there might be a little bit of inaccuracy there. It just depends on the concavity. If it's really has a really strong concavity at a certain point, it might not be quite as good of an estimate if you have something that doesn't have much concavity. Also notice that the one that I drew here was an underestimate or an overestimate. We're going to see in the future that if you have a concave up situation, then this will be an underestimate. If you have a concave down situation, then this would be an overestimate. An x cubed situation when V is positive is a concave up. So these are a little bit lower than the actual value. If you plug them in, you could check that out and find that out. Hope this helps.